Welcome to homework.
Hi there. So for this problem, we're told that the magnetic poles of a small cyclotron produce a magnetic field with a magnitude that is given, and that magnitude is equal to 0.80 Tesla. And the poles have a radius that also given, and that radius is equal to 0.45 meters. So for part A of this problem, the question is, what is the maximum energy to which protons, and we are given its charge and mass, can be accelerated by this cyclotron? And so, okay, now we know that the maximum radius of the orbit determines the maximum speed v of the protons. Now we need to use Newton's second law and what we know as the centripetal acceleration, which is equal to the speed squared divided by the radius. And so with that, we equal that to just simply the magnetic force, which is the product between the magnitude of the charge, the speed, and the magnetic field. So solving, if we equal these two expressions together and solving for the speed, we will have that is equal to just simply the charge, the magnitude of the charge, times the magnetic field, times the radius, and this divided by the mass. Now, the radius that we're given for this, well, let me substitute the value. So the charge for this is 1.6 times 10 to the minus 19 in units of coulombs. The magnetic field for this is equal to 0.80 Tesla. And well, let me just put it without the units in here. And this times the radius, that is 0.45. And this times, well, divided by the mass, which is 1.67 times 10 to the minus 27 kilograms. Then using our calculator, we obtain a speed of so the speed that we obtain from this is approximately 3.4491 times 10 to the 7 in units of meters per second. So remember again that what we are asked to calculate is the maximum energy. So we can calculate that maximum kinetic energy by its usual equation, that is 1 divided by 2 times the mass times the speed squared. So that will be 1 divided by 2 times the mass of the proton, that is 1.67 times 10 to the minus 27 in units of kilograms. And this times the speed that we determine, that is 3.4491 times 10 to the 7 in units of meters per second, and that to the square. Then from this, we obtain that the kinetic energy is equal to so the value that we obtain from this is equal to 9.933 times 10 to the minus 13 joules. So we multiplied this by factor of conversion in order to obtain this in mega electron volts. So we know that 1 mega electron volt equals to 1.6 times 10 to the minus 13 joules. And then from this product, we obtain a value of so the value that we obtain from this is 6.208 mega electron volts. So that's a solution for part A of this problem. Now for part B, the question is about what is the time for one revolution of a proton orbiting at this maximum radius. Now the time for one revolution period is just 2 times pi times the radius divided by the speed. So that will be 2 times pi. I'm going to substitute the values. You can determine that by using your calculator, okay? So that will be 2 times pi times the radius, that is 0.45 in units of meters, and this divided by the speed that we determined from before, that is 3.4491 times 10 to the 7 in units of meters per second, okay? So you just substitute that in your calculator, you will obtain the period. Now, for part C of this problem, the question is, what will the magnetic field magnitude have to be for the maximum energy to which a proton can be accelerated to be twice that calculated in part A? So, for this, we use the expression for the kinetic energy that we know is 1 divided by 2 times the mass times the speed squared. But also, we know that the speed is the one that we solved from part A, this expression right here. So we can substitute that in here. So that will be 1 divided by 2 times the mass times the expression for the speed, that is the charge, the magnetic field, the radius, and this divided by the mass, and that to the square. So simplifying this, that will be 1 divided by 2 times the charge to the square times the magnetic field to the square times the radius to the square, and this divided by the mass. And then if we solve for the magnetic field, we will have that is the square root of 2 times the kinetic energy times the mass, and this divided by the charge times the radius. And then, as you can see, the magnetic field is proportional to the square root of the kinetic energy. So if the kinetic energy is increased by a factor of 2, then the magnetic field must increase by a factor of the square root of 2. Then the magnetic field then is the square root of 2 times the initial value, which is 0.80 Tesla, which is the value that we are given. Let me calculate that. And that will be 1.13 Tesla. And that's the solution for part part C of this problem. Now for part D, the question is, for the magnetic field of 0.80 Tesla, what is the maximum energy to which an alpha particle, so we know we are given the charge and the mass for the alpha particle, can be accelerated by this cyclotron? So in this, we just use the same expression of before for the speed first. So that will be the product between the charge, the magnetic field, and the radius, and this divided by the mass. So I'm going to substitute the values in here. So the charge for this, we are given 3.2 times 10 to the minus 19. The magnetic field is 0.80 Tesla. The radius is 0.45. And this divided by the mass, and the mass for this is 6.65, and this times 10 to the minus 27. Then from this, well, the speed that you obtain from there, you just need to substitute it in the expression that we know for the kinetic energy, which is 1 divided by 2 times the mass times the speed squared. And the speed, we substitute the value that we're given. And that's it. That's the solution for this problem. Thank you.